In this video, I'm going to introduce the simple linear regression model, which is used for modeling linear relationships between two variables, which we'll call x and y. Y is going to be the quantitative response variable, also known as a dependent or outcome or output variable, and x is a quantitative predictor variable, also known as an independent or input variable or a covariate. In simple linear regression, these two variables play very different roles, so it's important to identify which one is which and to define them carefully. So for the running example throughout this chapter, we're going to use data on home prices, where y is going to measure the sale price in thousands of dollars, so that's going to be our response variable, and x is going to be the floor size measured in thousands of square feet, and that will be our predictor variable. A couple of questions that we can address using simple linear regression. One is, how much do we expect y to change by when we change the value of x? So in this context, we would be interested in thinking about the impact of floor size on sale price. So for example, a difference of 100 square feet, how much of an impact would that have on sale price? How much would sale price increase by if the floor size were to be increased by 100 square feet, say? And another question is, what do we expect the value of y to be when we set the value of x at 2? So in this context, it's what would we predict a sale price to be for a 2,000 square foot house. One thing to be careful of here is we're not thinking of this in terms of causation, so we're not saying that increasing the floor size necessarily causes the sale price to increase. We're merely modeling an association between the variables. So we're thinking in terms of observational data rather than experimental data. So we have to keep that in mind anytime we're interpreting the output from a simple linear regression model, that we're talking in terms of association and not causation. So here's some possible relationships that we might see in this type of context. So in the top left here, we've got increasing floor size leading to increasing sale price. So we've got a positive linear relationship. Each incremental increase in floor size leads to the same incremental increase in sale price. We've got a straight line. This one over here, I'm not sure that this would ever be observed in this particular context, because here we've got sale price decreasing as floor size increases. So this is perhaps an unlikely relationship. This one down here in the bottom left, though, instead of a straight line relationship, we've got a non-linear relationship, or a curvilinear relationship. And here for small houses, which would be the ones on the left of the graph, an increase in floor size leads to a big jump in sale price, and then a slightly smaller one, and then a smaller one still, and so on. So for large houses, changes in floor size don't really change the sale price much. And then finally this one in the bottom right, for small houses, there's not much of an impact on the sale price, a bit of an increase as floor size goes up, but then there's a big jump, and then another big jump for medium-sized houses, and then there's less of an effect for large houses again. So as far as simple linear regression goes, simple linear regression can handle straight lines, like the one in the top left and the one in the top right. We'll see later on in the course that we can model nonlinear relationships like the two in the bottom of this slide, but for now we're just going to focus on straight line relationships. So let's look at a specific example. So let's suppose that sale price is, on average, $190,300 plus a multiple of 40.8 times the floor size, when floor size is measured in thousands of square feet. As an equation, we write that in this way: expected value of y given x is equal to xi equals 190.3 plus 40.8 times xi. So this equation tells us what the sale price is on average for a particular size of house, but individual houses, their sale prices can deviate from this expected amount by an amount EI, which in statistical terminology is called a random error. So if we add that to the equation, now we've got an equation for yi given xi. So yi is the individual sale price. So it's 190.3 plus 40.8 times xi plus this random error. So these random errors, some of them are going to be positive for more expensive houses relative to their floor size, and EI will be negative for less expensive houses relative to their floor size. And we can think of the 190.3 plus 40.8 times xi, that's the deterministic part of the model. This part of the sale price is determined by these numbers, these regression parameters, 190.3 and 40.8, and the specific floor size for that house. And then the other part of the model, EI, that's the random error part. And that error is going to represent variation in sale prices due to factors other than X, other than the floor size, that we haven't measured and haven't put into our model. So things like the lot size, or the number of bedrooms and bathrooms, or the age of the house, how many cars you can fit in the garage, whether or not the house is close to schools. So all these other factors that we're not including in this model, those get bundled up into the random error and make the house more or less expensive than what we expect given its floor size. So let's look at some actual data, and I'll do this in R. So we'll read the data in and then we'll have a look at it. So down here we can see we've got 5 houses. The first one has a sale price of $259,900 and a floor size of 1,683 feet. And the next one, same sale price, but it's a little bit bigger, 1,708 square feet. And all the way down to house number 5 is the most expensive in this small illustrative sample, $285,000, and it has a floor size of 2,269 square feet. So I'm just going to attach that data set and then fit a model, and I'm not going to dwell on fitting the model just yet. We'll cover that in more detail later, but I just want to focus on a couple of numbers in the output. 190.318, so that was this part of the equation here, 190.3, and then 40.800, and that was this piece here in the equation. So the nice thing about simple linear regression is we can see everything that's going on in a scatter plot with the response variable on the vertical axis and the predictor variable on the horizontal axis. And so let's draw that scatter plot. So here it is down here in the bottom right of the R window, and we've got sale prices on the vertical axis, that's our Y variable, floor sizes on our horizontal axis, that's our X variable, and here's the 5 houses plotted. See, these two down here are the least expensive, smallest houses. This one up here is the most expensive, largest house. And then this equation, 190.3 plus 40.8 times x, geometrically that's the equation of a straight line. And so I can draw that line on the graph. So there it is. This straight line goes through the points and represents the deterministic part of the model, 190.3 plus 40.8 times x. So I said that this graph, we can see everything that's going on in the model. So what I mean specifically is, so this straight line, this is the equation, 190.3 plus 40.8 times floor. And then each individual sale price is given by the plotted points. And so let's just focus on this one here. This is the 4th house in the sample. It's got a floor size of 2,053 square feet. Okay, so you can read that off the graph down here, 2,053 or 2.053 in thousands of square feet. And then it's got a sale price of $270,000. You can read that over here. So that's its plotted point. But if we were to predict the sale price for that house based on this line, based on this simple linear regression model, we could multiply 2.053 by 40.8 and then add 190.3, and that would give us a number that would be right on this line, so right at the end of this arrow here. And then the difference between the two, the actual sale price, which is the plotted point, and the predicted sale price, which is the point on the line, that's the random error piece of the model. Okay, so that's what I mean when I say you can see everything that's going on in this graph. So in general, this is the simple linear regression model equation and its representation in a scatter plot. So the line is given by the equation expected value of y given x equals, and now we're going to use a little bit of notation, b0 plus b1 times x. And b0 represents the expected value of y when x equals 0. If I plug in x equals 0 into this equation, the last piece of the equation, the b1 times x, would be b1 times 0, so that would go away, and we would be left with expected value of y given x equals b0. So b0 represents the y-intercept. So in this picture here, when x equals 0, over on the left of the graph, y is equal to b0. So b0 is the y-intercept. And then b1, this is the slope of this line. And the slope, that's often taught in high school as rise over run. So it's the change in y divided by the change in x. That's the slope. So the higher this number, the more steep this line would be, and the lower the number, the more shallow it would be. So that's the simple linear regression model. And what we'll look at next is how do we get these numbers, these parameters that I mentioned, the 190.3, that's the estimated intercept, and 40.8, that's the estimated slope. How do we get these numbers from a particular data set? So we'll look at that in the next video.